Good afternoon, class. I apologize for the delay, but here's the couple slides over heat treatment and what to expect from ferrous alloys. So some of the terms that you need to become familiarized with are terms like annealing, normalizing, quenching, not solutionize quenching, but more quenching to harden, tempering, phase diagrams, and the isothermal transformation diagram. So first, I know I've talked about it a little bit, but here I have the a graph that represents the iron-iron carbide phase diagram. And what this particular diagram illustrates are the various phases that are present in an alloy system based upon the temperature and the composition. Okay, this does not take into consideration air cool versus quenching. This particular diagram, let me pull up a, let's see, do red. This particular graph here shows three different types of transformations that occur. The first one is up here in the top left corner, and that is called a paratectic transformation. That transformation, you are going from a liquid and solid phase, so solid 1, so you're going from a liquid plus a solid 1 phase, and it's going to transform to a completely different solid. For this transformation here that we're looking at, you're going from a liquid plus delta, which is your body-centered cubic structure of iron. Since iron is allotropic, this is the first body-centered cubic structure iron sees as it cools from liquid metal. So in this region right here, you have liquid plus delta, and then it branches down and it forms what we've been talking a lot about as austenite. So you do not have a delta phase in your austenite in this region. So that would be a paratectic transformation. Okay. The next type of transformation we can talk about is, let me get a different color here, let's do purple, is going to be the eutectic transformation. And that's going to happen right here. And this is typical for all cast irons. You are essentially going from a liquid phase to a solid phase containing austenite plus cementite. Write that real quick. And that is your eutectic transformation. This guy right here. Okay, like I said, it's going to be cast irons. The reason why is because at this particular eutectic transformation point, you're looking at a carbon content roughly around 4.1 to 4.3 weight percent. And as we've been talking about with carbon steels, a lot of your steel alloys do not exceed 1.5% carbon. Your next transformation is going to be the eutectoid transformation, and let's see, green shows up well, and that is going to be in this region right here. In your eutectoid transformation, we've discussed the term hypo versus hyper eutectoid. This is around a 0.8 weight percent carbon. So your eutectoid steel. This is where you are going from austenite to, which is one solid, to two different solids, being ferrite and cementite, Fe3C. Okay. Okay, so that is the transformation of a eutectoid. transformation. So how does this differ from a IT diagram? Well, in this case, I chose an IT diagram for a 1080 steel. These particular diagrams show the time required to transform the austenite from beginning to end as a function of temperature. Now, what are we transforming austenite into is going to either be martensite, bainite, or perlite. So this particular diagram is a is like I said, for 1080 steel, which is a high carbon steel. This also is known as a eutectoid steel because it's right at about that eutectoid composition of 0.77 to 0.8 weight percent carbon. So how does this play a role when we're talking about heat treatment of steels? Well, there's two different areas that are of interest when we're looking at this particular diagram. And the first one is going to be this solid red line that you see right here in this region. Okay, you notice that this curve has a nose to it. Okay, and that nose, if you draw a line right through the middle, the upper portion of this nose is going to address and let you know that you have the transformation of austenite to P for perlite. Okay, anything below that that solid red line, but before this red dashed line, will then give you bainite, and that's going to be B for bainite. Okay, for this particular steel here, you cannot form bainite without forming perlite. Okay, there's going to be a trick to forming bainite, which I will show you guys here shortly. The other transformation is going to be being able to quench below this solid, this dashed red line in order to form martensite. Okay, that's where martensite forms. So looking at this particular diagram, you can look at and see several different types of heat treatment processes that are not given in a phase diagram. So the difference, we are looking at temperature, the same as we did in the phase diagram, but in this particular case, the carbon content of the alloy is known. So now it's a matter of how do we quench, how do we heat treat, and that is designated by the time down here in seconds. So for a furnace anneal, same thing as shutting the furnace off with the samples in it and allowing everything to cool. This would be the trend line. It would take forever for it to cool down. Okay, so here's 1 week. All right, this is exaggerating, but here's 1 week's worth of time. So this time scale down here is a logarithmic scale. So in 1 week, the front portion of this nose is your start. Okay, so this is the start of where austenite begins to transform into something else. Since we are talking about a eutectoid transformation in this case, your austenite is transforming into perlite. Okay, so this region here, like I said, the first dark line is going to be the start of that transformation. The slight dashed line in the center is your 50% mark, and then the second solid dark line is your finish temperature. Your finish transition line. So in order for you to have 100% perlite for a furnace anneal, not only does it have to cross the first transition, but it has to cross the second transition, at which this point you can quench in oil, water, anything else, and you'll still have a pearlitic microstructure as shown here in the image. The lamellar spacing is is distinguished. You can see, how the interlamellar spacing between the ferrite and cementite are spaced out, which would be coarse pearlite structure. For a fine pearlite structure, we're going to go into normalizing. You can see now in this microstructure, the pearlite spacing is not as distinguished. Both of the images that I have shown you are at 1,000 times magnification. So this also being at 1,000 times magnification, the grain size is smaller. The interlamellar spacing is also smaller. And a normalizing would just essentially be pulling the sample out of the furnace and allowing it to air cool, as shown by the blue line here. So in this case, it began to transform here, and within, you're looking at, let's say, between 5 and 10 seconds estimated, you're looking at about a fine pearlite structure, versus the previous example, it took about a week and you had coarse grains, coarse lamellar spacing. So this would be another example of how you can determine the heat treatment of a particular steel. Looking at a quench, you want to be able to beat the nose of the curve, because if this particular line were to come across any portion of this nose, then your austenite is going to transform into ferrite, pearlite, and then the remaining amount of austenite will then transform into martensite. Okay, so it would be an inadequate quench, which means you didn't quench fast enough. So if I wanted 100% martensite, I have to make sure my quenching time, I have to be able to beat the nose. In this case here, I'm able to quench to room temperature in less than 1 second. Okay, so that's a very fast quench, which you can reach using water or oil. Once again, it's going to depend on your carbon content. But nonetheless, what you see in the microstructure is a martensitic microstructure, as quenched or untempered martensite, also at 1000x magnification. Well, when we have a material like this, it tends to be brittle. So in order to, very strong and brittle, but in order to gain a little bit of ductility out of it, you end up tempering it. So here's what a quench and temper, where the tempering temperature is at 1075 Fahrenheit. Once again, following the blue line, you quench and then you raise the temperature and you allow it to just sit there for an X amount of time. The longer you hold it, the softer your material becomes. So once you quench, you have essentially transformed all of your austenite into martensite. And by raising the temperature again, you do not form austenite again unless you went above the AS line, which is your austenitic start temperature. So if I go above that line, then I have re-austenitized my material. So I stop short of that. We're going to be just at 1075, and I hold it for a period of time, and then I quench again. And in that time frame, now I have tempered martensite. And you can tell it's tempered martensite because it has a fuzzy appearance. The needle-like structure isn't as distinguished or defined as the previous slide. So that would be how you would achieve a tempered microstructure. Now, depending on your tempering temperature will define how, I guess you can say, undistinguished your needles become. The lower your tempering temperature, so if I were to come and just go right above the martensitic start temperature for tempering, I would still have some designation of defined needles. But because I was at higher temperature, I soften the material more, diffusion's allowed to occur, so the distinguished needle structure kind of disappears, giving you this this type of morphology. So how do I form bainite in a material that I can't quench it to get bainite because I'll form martensite, and I can't allow it to furnace cool or normalize because I form perlite. So once again, if you wanted to form bainite, which is, once again, it's going to depend on what material properties you're aiming for. But what you could do is you quench and then hold, quench fast enough to beat the nose of the curve, and then you can hold at that temperature to your desired amount of bainite and then quench the rest. So in this microstructure you see, your feathery bainite is your dark microconstituent, and the tan colored regions are your quenched martensite. Okay, bainite will etch darker using nitol for your microstructures, and that's why your martensite tends to have a tan color to it. Your feathery bainite also forms in your prior austenitic grain boundaries. So if you were to kind of just follow this around, that would be more than likely a prior austenitic grain boundary here, and this is another one right here. Okay. In this particular case, because I do have bainite and martensite, according to the picture, this is at 1000x. It looks kind of 50-50. So once again, after you quench and you stop here and you hold it, you're holding it just long enough to reach the 50-50 mark in this transformation curve before quenching. Okay, so it took me half a second, almost 1 second, to quench to 900 degrees, and then I held it there for 3 seconds, and then I quenched the rest of it to room temperature in order to form this microstructure. Now, we know that feathery bainite has more of mechanical properties associated with that of perlite. Okay, it will be slightly harder, but you do have more ductility out of it. For lower bainite, when you quench, you're now holding, and now look how long you have to hold in order to form bainite. So instead of holding it for 3 seconds, which we would have done for upper bainite and quench, this would have just given us pure martensite. But in order for us to form bainite, which would give us better ductility than martensite at a slightly reduced strength, in order to reach 50-50 in this case, we have to wait for 1000 seconds, then quench. And that produces your lower bainite, which have more material characteristics of that of martensite, hence the needle-like structure. So those are your types of heat treatments associated with an IT curve, not the phase diagram that would give you these microconstituents in the microstructure. So for the assignments, please review the material over the ferrous alloys. I will be posting a quiz that'll be due at the end of the day for Sunday, March 26th. I'm sorry, March 28th, not 26th. And then your first assignment was due, that was your homework assignment. And the second exam, once again, is postponed until April 9th, starting at 1 o'clock. And it's going to cover any of the material pertaining to microscopy and ferrous alloys from your basic microstructures, heat treatment, and the soon and upcoming presentation on manufacturing processes. Okay, thank you for your time, and I'll get the other presentation posted shortly. Thank you.